Okay, so welcome back. So having talked about how to, we already got one solution for how to specify the response probability, or P of X, or the probability the Y is equal to one, or, this probability here. And in the linear probability model, that would just be, X times beta, a linear function of the parameters, and just some linear index X times beta. That would be the probability. The problem was, we got, predictions outside the unit interval. We got negative variances, inconsistent standard errors, or, because of the heteroscedasticity and so on. So we may actually want to modify our model so that we can ensure predictions inside the unit interval. And one obvious thing would be simply just to say, instead of the prediction being, X beta, it would be some function g of X beta. That's called a linear index model, okay? And then the question is, how do we specify this function g? Well, g should really be a function that maps that linear index into 0, 1. So obvious choice is actually a conditional distribution function, and that's actually where we are going. Okay, this is the most usual choice, and then depending on the choice of that CDF for whatever distribution that is, you get different models. So you just get different DGs depending on whether you choose like a normal distribution or a logistic distribution or some other distribution. And so then the next question arises: what does it mean to choose that distribution? And it can be actually useful to give that model that resolved in such a functional form for the choice probability a structural interpretation. By structural, I mean, we have some kind of underlying economic model that resolved in such a functional form. So one such model is the latent variable model. Okay, in that model, there's a latent variable y star. Y star is not observed. It's a latent variable, means that it's kind of, it's not observed. Okay, that latent variable is a function of X beta and an error term. Okay, so it's like X beta plus this error term. Now, if you observed y star, well, you can just do a linear regression, regress y star and X, and you would be able to estimate beta naught. Okay, by simply linear regression, but we don't observe y star. So what is the imputation here of y star? Well, you can think of it like it's a net utility of choosing alternative one. Okay, and if you do that, well, then it's natural to have the observed outcome being 0 and 1, our observed outcome variable, our binary response variable y, being basically equal to 1 whenever y star is positive. Okay, so this is like, if you think of y star as being, the net utility of alternative 1, the outcome where y is equal to 1, then it's like, doing utility maximization in some sense. Okay, or profit maximization, or whatever, this y star is supposed to represent. So if you have a model where some deterministic part of utility is, it's a linear function X beta, and then there's some error term that is like an unobserved component of that latent index, well, then that's kind of a structural model that you can start out with. Okay, now it turns out that if you do that, then then you get a choice probabilities that are between 0 and 1. And that's what I'm going to show here, right here. So we can derive that choice probability from these two equations here. So here we got our choice, response probability. The probability that y is equal to 1 conditional on X. That's the same as saying the probability that y star is positive, right? Because y is equal to 1 whenever y star is positive. So we just substitute this this condition in here because it's completely equivalent to y equal to 1. Okay. Now the next step is simply just to substitute in our model for y star in the place where we have y star down here. Now I've moved a little bit around. This is going to be x beta 0 plus epsilon, but then you can kind of subtract x beta on both sides of the equation, and then you get this. Now, what is this? This is a probability that this stochastic variable epsilon that has some distribution we've not specified is greater than the negative of x beta conditional on x. That is the same as 1 minus the probability that it's smaller than minus x beta, okay? I mean, these two outcomes either can be smaller or it can be bigger. So the probability that it's smaller is 1 minus the probability that it's bigger, okay? So this is what is going on here. And now what is this? This is really a CDF, or cumulative density function, okay? And then for epsilon conditional on x. So really, once you've specified the distribution of those epsilons, you have specified what G is. Okay, so if you're assume this is normally distributed, well, then this would be the CDF of a normal distributed variable. Okay, so and these things we can calculate. So by specifying what the distribution of the error term is and specifying the model like we have done, we have a full parametric specification for the response probability, which is kind of what we want in order to be able to explain the outcome, the probability of y equal to 1 conditional on x. Now we can move a little bit around. If G is a symmetric distribution, then this simplifies. And I have a little bit of a drawing that kind of shows this, but this is kind of in some sense like a trivial step. But let's just have a look at it, okay? In case you're not like ready to do heavy duty gymnastics with distributions. There's a nice picture. Well, this is a picture of a symmetric distribution, and I apologize here for this label here. This shouldn't really be the density, so the derivative of this function. Okay, so it's not the cumulative density function, because that would look like this S curve, right? Which is like the area below the curve. So this is like the density for that particular variable epsilon, and so the area under the density, well, that is what is the cumulative density, right? So I mean, so that integral from minus infinity to negative x beta, that is what G of x beta is, or the probability that epsilon is smaller than minus x beta. Okay, now this 0 here in the middle, right? And this distribution is drawn so that it's completely symmetric around 0. And many distributions are like that. For instance, a normal distribution. And so this means that this area here and this area here has the same size. In other words, what we have here is G of minus x beta. Well, over here we have 1 minus x beta, right? Because this is what is this? Well, all this area over here, well, that's G of x beta, right? That's a probability that epsilon, or set it's called here, is smaller than x beta. Okay, so to get the probability that it's bigger than x beta, well, then you have 1 minus that. Okay, and this is essentially what is going on. So due to the symmetry, we can replace G of minus x beta with 1 minus G of x beta, and then you basically you get this step. So this is the last step, is just due to the symmetry around 0. And of course, it only applies if that distribution is symmetric. Otherwise, you would have to work with this response probability, which is not super. It's much harder to compute. It's just a little bit cleaner to work with this. Okay, so moving on. Now, we now have a expression for the response probability that depends on this functional form for G. And we already talked a little bit about parametric models, right? That would be, we know G up to the set of parameters, and then we would just try to see if we could estimate the parameters, in this case, beta. But maybe you know, maybe the distribution G or the CDF of epsilon, well, that has parameters too, right? Distributions are usually indexed by, from a normal distribution, you would have like mean and variance. Oftentimes we just assume that the variant, that the mean of the error term is equal to 0. Otherwise, you can't really get identification. You're all used to that from the linear model. Like, you would assume that epsilon is conditional mean independent of um, has conditional mean equal to 0, right, given x. Um, so we're used to the, what about the variance? Okay, what is the variance of the error term? I mean, in a regression model, that could be a lot of stuff, right? I mean, that could be many things. It could be, if you have a lot of a variation in y, well, then you're gonna that you cannot explain. Well, it's going to be in epsilon. Okay, so there's potentially a parameter to estimate here that kind of determine what is that variance if we were to choose a normal distribution. See, the problem with binary response models is that we cannot really identify that scale. We cannot estimate. If we cannot identify, well, we cannot estimate. Okay, we would be able to easily identify the scale of the distribution or the variance of the distribution of epsilon if we were to observe y star, but we don't. We only observe y. Okay, so we have to estimate our model using this response probability. It turned out that the response probability isn't. That it turns out that the variance in that epsilon is not really identified. I'm going to show you this formula just in a few equations here. So here's an example. Here's me trying to show that in a simple way. So remember, we have the response probability from the latent variable model being, the probability that y star is greater than 0. Okay. So here I just took our y star and then I multiplied all the coefficients and the error term with some positive constant c. Now I can easily just divide both sides of this inequality with this positive number, and it's still going to hold. It's still going to be true. Okay. So you're going to get this equation here. Now, this is the same as saying that really you can scale up and down the variance of this if you scale up all the coefficients at the same time. Like, that's not the case in a linear regression model. Well, you can't just scale up all the coefficients and then you get like equally higher residual variance. That's going to give a different fit, but here it's going to give the same fit. Okay, so this, in other ways, we have some subtleties about identifications we're not really used to think of in the context of the linear regression model. So the problem here is basically that the response probability does not change if we both scale up the variance of the error term by multiplying with some constant and doing the same thing with all the coefficients. Now, I mean, these response probabilities, I remember from the previous video that we derived the conditional distribution of the observed variable y conditional on x, and these response probabilities were there. Now we're going to use that for maximum likelihood. So the likelihood function depends on those response probabilities. But if those response probabilities do not change when we change the parameters, we got a flat likelihood function. And in other words, you got lack of identification. And in the jargon of chapter 12 of Woolrich, it's like, there's not a unique maximum of the likelihood function, okay, or the objective function. So that's not good, and that means lack of identification. So what we can, the problem here is really that beta naught is not really identified. It's identified up to a scale factor. You can't identify it separately from the scale of the error term. Okay. Now, identification, without identification, you can't estimate consistently. So we need to obtain identification. What people do as a solution is we normalize the distribution of epsilon, for example, by assuming some fixed variance. We could also assume like a, coefficient on explanatory variable number 1 is 1, or do some other normalization, but we need to make a normalization. Okay. Otherwise, we lose identification. So here's an example from Probit. Okay. Now Probit, that's what happens if you assume that error term is normally distributed. Okay. Now I'm going to assume here that our error term in the latent variable model is, conditional on x, is normally distributed with some variance sigma 0. Okay. Now sigma 0 can be anything. It has to be positive, but so this would mean that we would try, if we were to estimate this model, we'd try to estimate both beta and sigma. The question is that even possible? And well, we're going to show that's not the case. So here, I essentially just took the same steps as before, deriving the response probability. Now for this latent variable model, where I specified what epsilon, what distribution epsilon has. Okay, the normal distribution. So we got, our response probability here, and then we can, rewrite that again as 1 minus the probability that epsilon is smaller than minus x beta. So we get like basically a CDF of epsilon. And now, since this is normally distributed with that variance, well, you could divide both sides with sigma. And then you get something that is standardly normal distributed. So now we have a very nice, functional form for that CDF. That's the CDF of the standard normal, and we can, that's something you can look up in your ask Python to evaluate, right? Or you can calculate that as the integral of the density, and which is given in closed form. So we can evaluate that guy, right? And so now we have a fully specified probability for y equal to 1. That is 1 minus that probability. And then because of the normal distribution actually being symmetric around 0, well, then you can do the last step just like we did before. Okay, so what you see here is that the probability that y is equal to 1 conditional on x is equal to the standard normal density that does not have any parameters. Okay, does not have any parameters. That's just fixed. Okay, so that functional form is fixed. But then it depends on x beta times beta naught divided by sigma naught. Okay. So again, you see if you scale up both beta and if you and sigma with the same constant, well, it's going to disappear here. In other words, it's really only the relative size of beta divided by sigma that matters for the response probability and thus for the likelihood. Okay, so you really need to make some kind of normalization in order to make to identify the parameters. We cannot identify beta and sigma squared separately, only their relative size. And this is in contrast to the linear model, right? If we were to observe this y star, then we would be able to estimate both the betas and the variance. It doesn't really matter that much because in the end, all we're really interested in is the response probability. And since the response probability is really indexed by beta divided by sigma, that's really all we care about estimating. So this is just a normalization. It's without loss of generality that you have to make this assumption. Okay. So, but it's really important to keep in mind. So you can't really, you can't really estimate both things. And also, it gives you also a little bit of reassurance that just assuming that that epsilon had a variance of 1 is not really a strong functional form assumption. It's a normalization assumption that you need to make. Okay, so that's pretty cool. So, given what we usually do is with scale, make this scale normalization, and then after the normalization, beta is identified. Okay, so we essentially just assume that sigma naught is equal to 1. Okay, and then you would have beta. That sigma just disappear everywhere. Okay, and we don't worry about it. Okay? This is also important to have in mind when interpreting beta in binary response models, because it's not only the case for Probit, it's also the case for other binary response models where we have we make some assumption about the distribution of the error term to get our response probabilities. So to get our G functions. For different G functions, well, you will have different sets of parameters. You have different variances. Okay, so there's something called the logit. I'm going to talk about it in just a minute. That has a different variance compared to the Probit. So this means that you would have estimates that are potentially very different, even though they're they are giving the very, very similar predictions about what the response probability is, or the marginal effects of changing or whatever variable has on the response probability. So that's very important to keep in mind. It also means that we cannot, it's not like the linear probability model where the size of the parameters says something about the magnitude of the effect. This is not the case here. I mean, a very, very small parameter, that could just mean that we have normalized with a very small variance. Okay, so you can't really interpret this. What you can interpret is by, for example, comparing the relative size of two parameters of two explanatory variables, say xl and xk, two different parameters. Okay, so if we just let the coefficient on xl be beta l and the one on xk be beta k, well then what you would estimate, well that would be that ratio, right? Because that's what we potentially can identify. Well, then the relative size of those two estimates is gonna the sigma is gonna cancel out. So regardless of how we basically how we normalize that variance, you're gonna get the same ratio. Okay, and really what is matter for the predictions in the model is these ratios. Okay, so so that was kind of Probit, our Probit example. But they're going to have other distributions, okay? And two very, very popular ones are, well, we have seen Probit, but there's also something called logit. And logit is just another distribution. It's symmetric like the Probit, like normal distribution, but it has a little bit fatter tail. Okay, so now this gives rise to two different functional forms for G, where we would, in the Probit example, just have the standard normal density for being our G function. Then we would, in the logit model, we would have the standard logistic distribution. Maybe I'm sure you know all about the normal distribution, and maybe some of you also know about the logistic distribution. But I'm going to show you the difference in just a minute. They're actually quite similar in terms of the shape. We can also calculate the derivatives of these, and the derivative of a CDF with respect to the random variable. Well, that is a change in the random variable that is equal to the density. Okay, so the density, so the derivative of G for the Probit model, that's equal to the standard normal density, where we have like this closed form expression. Okay. For the logit, well, you can see this is really easy to differentiate. I mean, this is, by the way, a very nice thing about the Probit is that you got, or the logit, you got this nice functional closed form functional form for easy to express functional form for the CDF. You can also express it like this, and you can, I mean, this is a nice pencil and paper exercise if you want to play around with exponentials, but it's going to give the same. This guy over here has actually a numerical benefit in the sense that if you have, say, set here, that in our model, that will be x beta, right? So if x beta becomes very big, well, then you have an exponential of a very big number that's huge, divided by the exponential of a very big number, of a big number that's huge divided by huge, and then computers tend to give up. In those situations, then it would be much better to have 1 divided by the negative of big, which is small, right? So then this is going to be much more well behaved and closer to 0, and the probability would be approaching 1 in that case, right? And the computer would not have any problems dealing with that. Okay, so this is more numerically stable, and it matters when you do the implementations of this model whether you use one or the other. Okay, even though they're theoretically identical, they have very different numerical properties on a computer. These are the kind of nice things you will experience when you do implementation of various things in economics and econometrics, that things can be different on a computer than in theory. But you know all about that. It's also pretty easy to differentiate, and here's the derivative, and it's basically high school math, combinations of taking derivative of exponentials and fractions, and I'm sure you can do that. So that's a derivative of this function with respect to a change in set. Okay, so I mean that seems reasonable. Or you can also do this expression. It's the same thing. So now we have like functional forms for our g function and its derivative, or the corresponding density. So why don't we try to implement that in Python and display the results, look at how they look like. So here's a Python implementation of what you saw on the previous slide. Okay, so essentially there's just 2 functions, g and capital G for the CDF, and small g for the density. And then it takes the input set, and then you can choose whatever model you want to do. If you do the Probit model, well, then you get the CDF of the standard normal. If you do the logit model, well, then you get the CDF of the standard logistic distribution. Okay, and likewise for the corresponding densities, you get the PDF of the standard normal. We could also have just typed in this expression here, but Python has some built-in function that does that. Okay, or if it's a logit model, well, then we basically use the expression here that we had on the previous slide. So exponential of set divided 1 plus exponential of set squared, which is what we have here. But this is identical to this expression, which is kind of showing that really that distribution is completely symmetric around 0. So it doesn't matter if you put in set or negative set, you're going to get the same density. I mean that's also what you get for the normal distribution, right? As long as we're working with something that's centered around 0. Symmetric center around 0. So this is why I'm making this transformation to basically take I take the absolute value and the negative of that, because then I'm sure that I'm not taking too many exponentials of very high numbers. I much rather want to take exponential of large negative numbers, because the exponential of a large negative number, that's going to be 0, and it's much more well behaved to have 0 divided by 1 plus 0 squared, okay? Compared to having overflow, which would be infinity divided by infinity. Computers ask, what the hell is that? Sorry, my French. So here's an attempt just to do a little bit of graphing of those 2 functions. It's not really worth spelling out what it's doing. It allows you, I want to say one thing, it allows me to have different scales on the logit distributions. We're going to use that in just a second. So that's the sole input. But otherwise, it's like 2 plots. That's the CDF for logit and Probit. And then there is, don't think about those. I think we should probably delete that. This is the density. So this is the density for the logit and Probit. Good catch. Okay, so I was copy pasting from a previous slide. So let's call that PDF. Okay, good that we're discovering stuff. Okay, so this is really what is going on. I'm making like some grid of set between -4 and 4, and then I'm plotting these two functions for both Probit and logit, and so here's what it looks like. Okay, so we just don't have the room for the output. Now these are the unscaled distributions of logit, which is like this you know, what is, I don't even know what that color is. Does it have a name? It's ugly. The blue one, well, I recognize that is Probit. Okay, so we see here that the Probit, the CDF of Probit is much steeper. It looks, you know, even more like the indicator function that compared to the logit CDF. Okay? And this means that when you have a small change in X beta, well, in the Probit model, you're gonna quicker, or you're gonna faster change from a small probability to high probability, right? For the same change in X beta. Okay. And another way to see, I mean, you can also look at the densities. Okay, this is kind of, it's very clear when you look at this that the variance of the logit is simply just bigger. The variance of that epsilon is bigger. But remember, we were, you know, now we have two different models that have two different variances. What we have shown in our quest through all these identification issues was that this just doesn't matter. This doesn't matter for our response probability, what that variance is. Just as long as we, you know, scale up the coefficients beta with that variance. Okay? But you can imagine what it means. So if you look, first estimate a Probit, and then you estimate a logit that has a larger variance. And we were only able to identify, you know, basically the beta divided by that variance. So then it would look like, you know, if the variance is bigger here for the logit model, well, those coefficients that we have estimated is going to be looking different because they have different scaled by a larger variance. And let's return and see if we can actually recognize the patterns once we start estimating logit models and Probit models and comparing. Now that was just a scale thing. So we kind of, you know, agreed that that's not really what matters for estimation. But what about the functional form, the shape of those distributions? That's really what matters for how well the model is going to fit. Okay, or what the predictions of that model is. This Probit and logit really very different, except from that scale. And the answer is not really. Okay, we can, for example, I mean, one obvious thing would be say, okay, why don't we just scale the variance down a little bit on that logit distribution, which is exactly what we can do if we change this parameter here, then it scales down the variance of that logit distribution. Okay, so I allowed for that. You could go check it out what it really means. But if we were to say what about this variance? Say if it was 2. Okay, it looks like this. Well, oh, okay. No, this is, I'm putting it. It has, you have to scale it with the variance. So now we make the variance divided the variance with 2. Now it's smaller. You can see they're more similar, right? But not really, you know, similar enough. Okay. What about if, you know, in 1.5? So now they start to become very similar. And actually, we can actually just calibrate these two functions to have the same, basically have the same point here by simply divided by set the scale to 0.25, which is the density at 0 for the standard normal divided by, or the standard logistic distribution divided by 0.4. And if you do that, you get something that looks like this. Okay. Now they're very, very, very similar. Okay. and well, they're identical at this particular point. Okay? So you see here we can the logit and the logistic and the normal distribution is very similar in this shape. Um, the logit the logistic distribution has a little bit fatter tails compared to the logistic distribution, but they're both symmetric and bell shaped, and it's not like one is going up and down or is skewed or anything like that. We have very similar predictions. So the fatter tails means that you kind of allow for a little bit more probability for more extreme outcomes compared to the normal distribution, but not a lot really. Okay, so this kind of leads to the slide of the choice of whether it should, I'm just summarizing here, the choice between logit and Probit. So both of them give predictions of choice probabilities that are between 0 and 1, because this G function, the CDFs, are both, CDFs that has that property being between 0 and 1. And I mean, you can also see it in a graph. Here's 1 and here's 0. They're everywhere between 0 and 1, right? As they should be if they're CDFs. So this means that whatever x beta you put in to these functions, it's going to be resulting in probabilities that are between 0 and 1. Thereby, the conditional variances, the probability times 1 minus the probability, that's also everywhere positive. Okay. Now, another nice feature of these Probit and logit models and other models that has G being limited to the unit interval. Then the logistic distribution and normal distribution are very similar. So we've seen if we scale them, they are both symmetric. The logistic distribution has a little bit longer tail. The derivatives are positive everywhere. So it's like, just like the normal distribution that has infinite support in the sense that the density is positive from minus infinity to plus infinity. Well, it may be very small, but it's positive. The same is the case for the logistic distribution, actually putting a little bit higher probability for extreme outcomes. So they're also similar in that respect. It's not like a bounded distribution that is, say, only defined from, say, 0 to 1 or from A to B. It's from minus infinity to infinity. So in that sense, they're similar too. So generally, this shape is really identical. Or not identical, but very close. The scale is different in the standard version of these distributions. The Probit usually assume that the standard deviation is normalized to 1, whereas the standard logistic distribution, well, it doesn't have a parameter for the variance, but you can scale it up and down. But with the usual scale parameter being just one, then the variance of that distribution is pi divided by the square root of 3, okay, which means that the variance is 1.8. Now we can actually go back and see what happens if we scale the variance here to be make the scale being 1 divided by 1.8. Okay, and you can go in and check that what it's doing, but these two distributions have the same variance. Approximately, it was not entirely 1.8, but now you can see it has more mass here at the mode for the logit, because we kind of had to compress those more heavy tails, okay, to get the same variance. So, but putting the same variance, they come to look more like each other. Yeah, so in short, they are pretty similar. Okay, so the scale really we've seen when we talked about identification, well, that the scale really the scale differences of these two choices is going to be irrelevant, because we can't even identify that variance relative to the beta. So what we do estimate is beta divided by that variance, and we don't really care what that variance is. We also see that, as we'll see later, the average partial effects and the partial effects themselves, the change in how that response probability change when you change the explanatory variables, that will actually be similar for both Probit and logit, because those response probabilities are really a function of beta divided by sigma. We're going to look at that when we make a more thorough treatment of the partial effects. And also the ratio of different coefficients is going to be different across different specifications. Okay, so next step, having established identification, is going to be about estimation. Okay, you can't really estimate models if you can't identify the parameters. So we had to make sure that we can obtain identification. We can obtain identification when we make the scale normalization, setting, for example, the variance of the error term to be equal to, say, 1, for example, for the Probit model. Okay, so let's have a little break, and return and talk about estimation in the next video.